Okay, so our plan this week is to do a lesson today on reactivity, and it's a fairly short lesson actually. If you guys look at the notes I printed off for you, there's not a whole lot of them here. Then we're going to do a lesson tomorrow, and tomorrow's lesson is kind of like the climax of these three lessons we've done together in a group, where we're going to talk about how we can use electrochemistry to create batteries, essentially. So tomorrow's lesson is going to be a little bit longer in terms of notes. I'm making them right now. The reason why they're going to be longer is that I've got a ton of pictures, because one of the things I'm going to need you guys to be able to do is to look at a simplified picture of a battery and identify, well, what exactly is happening, right? So it's mostly identification. Um, like I said last week, really all of the math type stuff is done in like the first little section that we did, where you had to like do grams to moles and liters and all those formulas in the corner of your formula sheet. This next section here is not like that at all. It's just all theory. It's all memorization and knowledge. So that's the plan for today and tomorrow. A couple sets of notes. Wednesday, I want to give you a work day so that you can try to kind of practice up and do some of your assignments or your labs or whatever you haven't done. Have you guys all finished your quiz? Okay. Have we gone over it yet? Maybe we could spend some time on. I did that already with you. Okay. If we haven't, we should spend some time doing that next week Wednesday, or sorry, this week Wednesday when we have a free work day. Thursday we're going to do an activity where I've said this before. What I'd like to be able to do is create a battery using chemicals, and if possible, we'll just pop a battery, like a AAA battery, out of your calculator, and we'll hook up some alligator clips, and we'll basically try to run your calculator just purely off of chemicals. I've had that work before, so. And then Friday we'll have a work day, and then next week Monday we'll do a quiz on this stuff. You guys are late. Dr. Phil. All right, we're already started, just so you guys know. I'm recording just so. It's okay. We just started doing some review. Let's talk what we did last day then. It's been a little while, but last week on Wednesday, I think was our last day, I gave you guys a bunch of definitions. It's mostly words. So why don't I just write some of them out and we can informally try to remind ourselves of what they meant. No, it's this one here. It's topic 7, just not the right. Yeah. Okay, so here's some words we would have learned last day. Let's start with this one. It's known as reduction. Does anybody remember like what like the historical definition of reduction was from like thousands of years ago? Well, when you reduce something, what did it mean? Yeah, fantastic. Yeah, turn into a pure metal. For example, just IE right here. An example would be like say Al2O3. If I turn it into Al solid plus some oxygen gas, that would be known as the reduction of aluminum, where you take an ore, O-R-E, of a metal, and you try to refine it. You guys recall that? And then the opposite of reduction was oxidation. Oxidation. And this would be kind of the reverse process, where maybe you have like some pure iron, it was pure, and you add it to oxygen gas, and when you add it to oxygen gas, it makes an impure metal, something like that. Usually we have another name for this. We call this rusting. Rusting is kind of like a I-N-G. There you go. Rusting. Rusting is kind of a doesn't look like rusting at all. Fix that. R-U-S-T. I haven't used this pad in a while, so I'm kind of bad on this one. I tried the wired one for so long. So. Rusting is where basically something corrodes. Rusting, though, is usually referred to just specifically as what happens to iron, whereas the term corrosion is like an overarching term for anything that kind of does this oxidation process. So those are some of the original definitions, but chemists really kind of learned over time that those were kind of a little bit too broad. Actually, sorry, I should actually say the opposite. Those weren't specific enough because reduction came to be known as anything that involved the gain of electrons, which is where like the Leo and the Ger came from. If somebody gains electrons, it means this aluminum right here would have went from being a +3 ion to a neutral atom. And if you go from positive to 0, it must mean you've gained electrons, because that's how you get more negative as you gain electrons. Whereas here, this iron would have been a charge of 0, and then over here it goes to being in a compound, so it has a charge of +2. To go from 0 to +2 to become positive, the only way you become positive is you lose electrons. Well, why can't you become positive by just gaining more positives? Yeah, you change chemical species, the element would be different, right? Iron is supposed to have, according to our table, where is it? Number 20, 26. So iron has to have 26 protons. It can't gain 2 more protons because then it wouldn't be iron, it would be nickel. So it has to be the electrons. Now, what I'm going to talk about tomorrow then is the brilliant person who discovered, well, hey, if this guy right here has to gain electrons and adds more of them, and this guy right here is going to lose them, what happens if we didn't just like transfer them like hand to hand? And I gave the example last week of stealing lunch money. So let's say that I'm trying to steal electrons. I want to gain electrons. I am going to steal Sarah's lunch money, right? Well, I mean, in that case, if I'm gaining electrons, I am being reduced. And if she is losing electrons, losing her money, then she's being oxidized. So if you do it directly, that works just fine. But someone really clever said, what if we do it indirectly? What if we had the electrons go the other way around the circle? Rather than going directly from her to me, what if we make them go through a circuit? Well, that's essentially how you run like a light bulb or a battery or really anything along those lines, right? Is a circuit has the electrons run through it. That makes sense? So the other two terms we should talk about are the reducing agent and the oxidizing agent. We usually represent them with just Ra and Oa. If I am stealing Sarah's money, I am gaining electrons. But I'm actually the oxidizing agent. Even though I am being reduced, I'm the oxidizing agent because the oxidizing agent causes somebody else to oxidize. So if I'm the bully who's the stealer, I'm the oxidizing agent because I cause her to oxidize. And then if she's oxidizing, she's the reducing agent because she's the one who kind of lets the other person take their electrons. You guys get that terminology? All right, cool. Let's move on. That was more or less our day on last week, Wednesday. So today what we want to do is kind of keep building on this concept of redox. Redox is wherever you have both reduction and oxidation happening at the same time. So here's again those definitions. The oxidizing agent is the person who gains electrons. Because remember, GER. The oxidizing agent is the one that undergoes reduction. And then if you're lost by the reducing agent, that means that it's Leo. So I like this analogy here. I mentioned the idea of like trying to steal your lunch money. But maybe a better example would be like a tug of war, where there's like a fight for electrons, where I want to steal her electrons. I want to steal her lunch money. But sometimes there's a fight, right, where she fights back. And so really the question is, who is stronger? Am I actually a big enough bully to steal her lunch money? Or do I try to steal her lunch money and she slugs me back and says, no, get out of here? And really that same sort of concept happens in chemistry, where we actually have to figure out whether or not something, and that's the topic of today's notes, whether or not there will actually be a reaction. And that's the name today is reactivity, as to how reactive is an equation. Is it going to happen all the time because I'm such a big bully that I can steal her lunch money? Or is it actually possible that I can write a reaction on paper, but that it doesn't actually occur because I'm not actually strong enough to steal electrons? So the word we're going to use is spontaneous. If you guys are highlighting stuff here, use the word spontaneous or spontaneity. If we talk about spontaneity in like everyday life examples, someone who's spontaneous is one who's like, kind of just goes with the flow and just decides to randomly, hey, let's go to Mexico this weekend, right? Like that's a spontaneous person. It means something completely different in chemistry. Spontaneous in chemistry means that someone is in fact strong enough to steal the other person's electrons. So that's the goal of today's lesson. So more review. I'm doing tons of review to begin class, just because I really want to make sure you guys get these concepts here. Let's say that we've got zinc and copper 2 plus turning into zinc 2 plus and copper. Do you guys think we could label the oxidizing and reducing agents? Well, let's start this task. I would base it on charge. What is the charge on this solid zinc right here? 0, yeah. Zinc went from 0 to plus 2. Okay, so to go from 0 to plus 2, it means you must have lost electrons. So this one must have lost its electrons. If you lose your electrons, we call you the reducing agent. Whereas this copper went from plus 2 to 0, so it must have gained electrons. It's very redundant, right? Because it's the same thing over and over again. So that means he's the oxidizing agent. Well, if this reaction is going to take place, it means that the reducing agent must try to steal electrons. That says steal, by the way. I really can't write very well on this pad today. S-T-E-A-L. This guy's going to try to steal electrons, kind of like what I have in this little diagram right here. Oxidizing agents try to steal, reducing agents. Did I have that right? That's not right. This picture here is backwards. Because this arrow should really go the other way, shouldn't it? What was that? Yeah, transferred from a reducing agent to an oxidizing. We didn't do this backwards, did we? Zinc is going to an iron form like this. So zinc was losing its electrons. So it makes it a reducing agent. Yeah. And then right here, copper was going from 2 plus to 0. So if it's going from 2 plus to 0, it must have gained its electrons, which makes it an oxidizing agent. I think this picture of the textbook's wrong, but that just seems so strange because I just snapped it out of a book. Because, I mean, wouldn't you agree with my first one right up here? This guy right here is supposed to be, oh no, hang on, no, it is right. Hang on one sec here. The reason why, I'm not drawing this properly. This guy's supposed to lose electrons. This one's supposed to gain electrons. I should really read my words better here. So the guy who wants to gain the electrons have to go towards the one who wants to gain the electrons. There we go. It does fit the picture, just it's in the wrong order, hey? That's why I think I did it wrong. The oxidizing agent's over here. The reducing agent's over here. So long story short, is this guy right here a good enough guy for stealing the electrons? Is he strong enough to steal the electrons? Because if he is, then the reaction takes place. The reason why I need to point this out is that there are lots of reactions that could take place, but that don't. For example, right now, this table could try to oxidize. It doesn't, though. It doesn't just oxidize in front of us because the electrons are not strong enough to be able to be transferred from one to the next, whereas like other metals do have that ability. Maybe the best example I could give you would be iron versus gold. You know why gold is so valuable is not that it's rare. I mean, it's relatively rare, but the reason why gold is valuable is because it doesn't rust. And the reason why it doesn't rust is that gold does not like to lose its electrons. If there was like a king of the ring battle where I'm copper and you're gold and you're silver and you're all different metals here, gold would be like at the top of the list because it doesn't like to lose electrons. And because gold doesn't like to lose its electrons, it's like the biggest bully out there. And so if someone comes to him and says, hey, give me your lunch money, gold says, no. Right? And that's the reason why it doesn't rust. Whereas there's other metals that are kind of wimps out there, where like iron is relatively a wimp. So when someone comes up to iron and says, hey, iron, give me your electrons, it's like, here, take them. Right? Which is why iron rusts so easily. Does that make sense at all? Let me keep going here. Try another example here. Here's another picture just kind of illustrating the same thing here. Let's say that you have this Fe2O3 go to Fe solid. Based on our knowledge of oxidation and reduction, this is reduction because it's going from a solid to a metal. Right? Well, this will occur according to these circumstances. Reduction means the gain of electrons. It means this guy wants to steal electrons. Well, it means that whatever this reducing agent is right here, it has to be someone that he is capable of bullying. If iron right here is not capable of bullying him because you picked on somebody higher on the ranking list than him, then you don't win. Does that make sense? So what I need for you guys to do actually, can you find me your data booklets? What I'm trying to build towards today is that there's actually like a ranking system. When I think of this, I think of like, I don't know, UFC fighter ranking list, where there's the number one contender, then there's the second guy, then there's a third guy, and at the bottom there's the weakling. And what you're looking for is a table called the reactivity series, or the activity series, which is on page 4, right at the very, very top left-hand corner. I see that? It's the activity series under electrochemistry. And the long and short of it is this is like the world rankings for who's the strongest and who's the weakest. And like I was just saying about 2 minutes ago, you see who's on the very, very top of the table there? Gold. Gold is not valuable because of the fact that it's rare. It is, but it's more valuable because it doesn't rust. And the reason why it doesn't rust is that no one can steal its electrons because it's number one contender. Mercury is actually number 2, and then right after that is silver. which also makes sense because silver is also a very valuable metal, meaning that silver does not rust very easily. It's possible for it to rust, but only if the right circumstances come across. Right? And when you go further down the list, then you get down to copper. Copper also doesn't rust very well. It's possible to, but it doesn't nearly as much as if you get further down the list to, like, say, iron and zinc and chromium and aluminum. Those guys actually rust a lot easier. So this is actually like your world rankings, if that makes sense. So the top guy is the least likely to lose electrons, and the bottom guy is actually a wimp. The bottom guy, like, says, please take my electrons, I don't want them. Which makes sense because where on the periodic table is lithium? Top right-hand corner, left-hand corner there. You know how lithium becomes a +1 ion? The reason it becomes a +1 ion is that lithium has one extra electron. And it says, take it away, I don't want my electron. Whereas gold, although gold is capable of forming, of doing its electron bit, gold really is, it's more hesitant, it's stronger. So that's what I want to help you guys work with, is this table here. Okay, on this slide right here, I just want to talk about terminology a bit more before I get to the table. Oxidation and reduction are the actual processes. So they're like the action words, the verbs. Whereas the oxidizing agent and the reducing agent, those are the actual species themselves. So gold could be a reducing agent. The process of reducing is to gain electrons. So, okay, let's get to this slide here. This is kind of the whole point of today's lesson, is this table here. This is called an activity series, and when you think of it as being a fight for the electrons, this table will tell you who wins the fight. So, up in this top corner right here is your king of the ring. This is gold. Gold wants electrons. Gold does not want to lose its electrons. It holds on to them tightly. And so sometimes what we'll do is we'll talk about this guy up here as being the strongest. And this guy down here as being the weakest. You see how it says this is the increasing strength of reactant as an oxidizing agent? Okay, think this through here. An oxidizing agent gets reduced. And according to Leo says, Gur, reduced means you gain electrons. So gold is the one who wants to gain electrons, which means that if someone wants to try to steal his electrons, he says no. Whereas lithium right here, lithium is the guy who doesn't want to gain electrons. When someone says, hey, I want your electrons, he's like, sure, take them. Does this make sense? Okay, so let's try an example. One more slide here. Spontaneous. So the spontaneous reaction then means that the reaction will actually take place, that there is a winner to the fight and the guy is able to steal the electrons. Non-spontaneous means that the chemical reaction really doesn't occur on its own naturally. So, okay, here's our example. Let's say you put some zinc into some copper 2+. Let's try to figure out what could happen. So what we're going to do is we're going to write the reduction and oxidation half reactions. We're then going to locate these on the activity series and figure out whether this reaction will happen spontaneously. So here's how this would look. First, we want to write the oxidizing and reduction half reactions for zinc metal. Well, zinc metal would be zinc solid. And then copper 2+ would be written like this. What happened if we took some zinc, added it to copper 2+? Okay, well, zinc is currently with a charge of 0. So what should happen then is zinc should now become its charged molecule, which is 2+. So zinc goes from 0 to 2+. Okay, if you go from 0 to 2+, what happened to you? Did you gain or lose electrons? If you go from 0 to 2, you lost electrons. Good job, guys. Okay. I said last week, it's like you got a 50-50 shot at this. Like it's one or the other, right? So this guy would have lost electrons, which means that zinc is oxidized. So we would call him the reducing agent. Okay, well, reducing agents get oxidized. Oxidized things lose electrons. So if we want to use that bullying analogy, Sarah, you're going to lose some electrons. Who's going to take the electrons, though? Okay, well, zinc is the one losing the electrons, though. Who's going to take them? Copper, yeah. And so copper would be, say, me in this example. I'm going to steal the electrons. So copper was going to go from 2+. What's it going to turn into over here? Anyone want to take a stab at it? Yeah, copper with a 0 charge on it, which just means it'll be solid copper. which means that this guy here would be gaining electrons. Someone who gains electrons is the oxidizing agent. So I think what we've done now is we've written the reduction and oxidation half reactions that describe this situation. I actually have put them together in one big equation. What you may be asked to interpret is like how to write them one at a time. So if we only wanted to write the oxidizing half equation, it would look like this. Zinc solid would turn into zinc 2 plus. I'm only going to write the stuff about zinc. That's known as a half equation. Whereas the reduction half equation would be about copper. Copper 2 plus would have turned into copper solid. You see how like I'm really taking the equation that I had here, I'm just writing it like half of it at a time. Those are known as half reactions. Except I made one little mistake here. If zinc is going to zinc 2 plus, oxidize means it has to lose some electrons. How many electrons would you have to lose? Yeah. So we'd actually have to write 2 electrons over on this side over here, saying that 2 electrons were quote unquote lost. This is Sarah losing those electrons. But she's not just losing them, someone else has to take them. And we just said that copper takes them. So I also need to write some electrons in the copper half equation. Which side of the equation should I write them on? Yeah, because the 2 plus then takes them to become the copper solid. So this is how you'd write them as the 2 half reactions. Okay, now for the key question. So what we're seeing here is that zinc is going to be getting bullied by copper, and copper is going to try to steal his electrons. But now the question is, though, will this actually happen? Does copper have like enough oomph to him to actually be able to steal the electrons? Which means we now have to look at our list here and figure out, is copper above zinc? If copper is above zinc on our table, then yes, this happens, and the reaction will take place. So is copper above zinc? It is too, yeah.
What if it's not on here?
If it's not on there, we won't do it in this course.
Okay.
Now, there's actually a bigger table specifically the Chem 30 booklet that has way more reactions, and then that one probably still is missing a whole bunch. So I'll only ever ask you something that's on this table. So you just have to figure out which one is above. So because the copper 2 plus is above the zinc, let me just find this table here to make sure we're clear on it. Since the copper 2 plus is up here and zinc solid is down here, because this one is above this one, the reaction will take place. So sometimes what I'll say is I'll have my kids in Chem 30, I'll have them circle where your things are. Here's this one, here's this one. If it goes downhill, things naturally go downhill. So therefore this will be considered spontaneous. Whereas if we were to try to react this aluminum here with this silver, it wouldn't occur, because silver solid does not rust, just like gold solid does not really rust. So
even if it's just one above it,
if it went from like this calcium to this sodium right here, it wouldn't work, right? It doesn't really matter whether it's 1 above or 5 above. If you think of it as a world ranking, the number 7 does not beat the number 5.
Yeah.
Right? A loss is a loss. Okay. Let's try one more. Let's do one last example. I want to show you like where something is not spontaneous. So what we're going to do here is we're going to dip some gold in some hydrochloric acid. And the hydrochloric acid, all I care about is the hydro part of it, because the acid is based on this H plus part right here. Now, in theory, this should work. I've never been brave enough to tell my class that I'm going to take my wedding ring off and throw it into a beaker of acid, because in case somehow I'm wrong, or there's something else. I mean, some of this isn't pure gold. There's other things mixed in here. But in theory, I've already told you, gold should not oxidize or rust or lose electrons. So let's prove it using the table here. If I've got gold jewelry, that would be Au solid. If gold is actually going to rust or oxidize, it needs to lose some electrons. It's going to turn into Au 3 plus. That's the most common charge for gold. Well, if the gold solid is going to turn into gold 3 plus, which side do the electrons go on? The left-hand side or the right-hand side? Yeah, they always go with the positive one. So gold is going to need to lose 3 electrons. Well, those electrons aren't just randomly lost. They have to get picked up by somebody. And it says that there is an acid solution containing H+. So H+ is going to pick up some of those electrons. Question is, what is H+ going to turn into? Not H by itself. H actually comes in groups of 2. It's diatomic. And it's going to turn into hydrogen gas. Well, this would be bad. I take my ring off, I throw it into some acid, and it dissolves and turns into gas, hydrogen gas. Well, that'd be horrible. But this is actually the reason why gold is so valuable, is that it's one of the few metals that should not do this. I actually think I have some silver in the back. I might be able to try it with silver, maybe. I'll go take a look. I'll see whether I have some. Anyways, the long and short of it is then this is what the reaction should be, except this isn't balanced. Do you guys see on your table, the fifth one down, it goes 2H plus 2 electrons? We actually need to have 2 electrons and 2 H pluses to form hydrogen gas. So I've now written out my oxidation equation right here, because that's losing electrons. This one would have been my reduction equation. But the question is, even though I can say on paper that it's going to occur, will it actually happen? Is hydrogen strong enough to steal electrons from gold? Well, then when you go back to your table here, I'm just going to erase all this stuff here. Yeah, you're ahead of me here. We have hydrogen in this ion format here, and he is going to try to steal the electrons from gold. Is he able to? No. Gold is the king of the ring. He's the #1 contender, right? He is not losing his electrons. Right here, this is always going to happen. Gold is going to always try to pick up more electrons and stay gold solid. And so this guy right here who wants to steal the electrons, hydrogen can steal from lead, or this guy, or this guy, or this guy. He can totally try to do that.
What if it's exactly?
Well, if it's exactly across, then that's what it turns into. Yeah. So H could try to steal from this one, this one, this one, this one, but it's not stealing from that one up there. Does that make sense? So what we would do is we would say, even though I can write these reactions right here on paper, it's considered to be not spontaneous. So if I want to describe what you would observe nothing. Nothing will happen. Even though I can write the equation on paper, it doesn't actually happen. So that makes sense? Why don't you guys give me 5 minutes? Let me grab some chemicals back there. Let me try it. I won't try my wedding ring, but I'll see whether I can find maybe some of these metals on here, like silver and copper and stuff. Maybe we can try to observe these results and see whether or not the acid is actually able to dissolve some metals but not others. So why don't you guys take 5 minutes just to take a quick break or get organized. I'll stop the video here, and then meet me in the back. Does that work? Because that was my last slide, right? Yeah, it was. Okay.